The ultimate goal of emergency escape systems is safe escape from air vehicles under all conditions. Realization of this goal came a step nearer when, in November 1962, McDonnell Aircraft was awarded a contract under General Dynamics to develop a crew escape module for the F-111 airplane. This module was to be an integral part of the aircraft, with escape systems essentially independent of the aircraft system. It was to provide successful escape in flight regimes where escape had hitherto been considered impossible. Basically, the module was to consist of an enclosed two-place cockpit section and the upper portion of the fuselage and wing glove. A parachute deployed by catapult forces would provide for safe descent, and a pneumatic bag would attenuate ground impact forces. The entire module would be severed from the aircraft by shaped charges and propelled upward and forward by a solid propellant rocket. McDonnell's initial contract called for 23 flight articles, 14 interim modules equipped with ejection seats, and 9 production versions of the ultimate module. The interim modules, those with ejection seats, would provide for test flights of the aircraft itself, prior to safety of flight tests on the final article. The first flight crew module, Air Force One, was delivered in June of 1964. By July 1965, all of the interim modules had been delivered, along with 6 of the production test modules. Qualification tests of the production configuration had also commenced by this time. Wind tunnel studies had started in early 1963. Approximately 800 different configurations were tested in the subsonic, transonic, and supersonic ranges. For example, from February 1963 through September 1964, McDonnell conducted over 1,400 test runs in the plant's low-speed wind tunnel. In one series, a 7.5 scale model was coated with a fluorescent oil solution to aid in airflow visualization. To cover the entire flight regime of the aircraft, high-speed tests were carried on concurrently in the polysonic wind tunnel. More than 2,500 runs were made during the 18 months ending October 1964, including ejection tests with the 5% scale model ballasted to simulate full-scale ejection. At the same time, development work proceeded on the main parachute catapult system. 9 static bag stripping tests were carried out at the McDonnell Pyrotechnic Test Facility. Their purpose? To investigate the catapult's effectiveness in deploying the main chute with velocity enough to free the canopy. From truck-mounted fixtures, 9 more tests studied the same sequence at low speed. Although the chute muzzle velocity of 100 feet per second proved successful during initial tests, it was later reduced to 30 to prevent parachute damage. Other improvements included a new bag packing technique and the addition of brake ties between the canopy and bag for orderly parachute deployment. Meanwhile, at Naval Air Facility, El Centro, California, a 3-phase test was in progress. Phase 1 had used a cylindrical vehicle with a pilot chute to deploy the main chute. For Phase 2, a Mac-designed bomb vehicle was loaded aboard an RB-66. The bomb vehicle used a pyrotechnically actuated catapult to initiate parachute deployment. 41 such drops were made, and system integrity was positively demonstrated. The final phase began in June 1964 at Kirtland Air Force Base. Here, a boilerplate module was mounted under the wing of a B-52 and dropped at Naval Air Facility, El Centro. Altitudes and speeds were varied through a series of drops. On 27 June 1964, boilerplate number 3 made its first drop. Altitude, 16,000 feet. Airspeed, 215 knots. Separation was clean, but a right yaw developed with an accompanying right roll. Because of excessive pod asymmetry, inertia coupling occurred. Despite this phenomenon, deployment of the main chute was obtained, and recovery was completely successful. The tendency toward inertia coupling was overcome, finally, by replacing the stabilizing vanes with a stabilization brake-chute system. This modification was to first appear in November 1964 on boilerplate number 3. Much earlier, and simultaneously with the wind tunnel test, a special impact bag for cushioning landing shocks was being tested in the St. Louis area. An air-filled nylon fabric bag attached to boilerplate number 1 was dropped at operational speeds of the F-111 aircraft. On impact, special release plugs, attached with shear pins to aluminum orifices, released air at a predetermined rate. Although some modification of the porting was necessary, tests showed the bag to be capable of absorbing most of the landing shocks. By the end of October 1964, development tests of the impact bag, both on land and on water, were completed. The rocket motor of the module was development tested at the Mesa, Arizona facilities of Rocket Power Incorporated. Within 4 months, 16 static firings under varying parameters of temperature and stress were completed. This single-thrust rocket was later replaced by a bi-nozzle rocket to minimize adverse jet effects. Meanwhile, during the fall of 1964, the first phase of the 2-year sled test was underway. At Holloman Air Force Base, New Mexico, the first interim crew module configuration, equipped with 2 ejection seats, was successfully tested in October. Test vehicle was boilerplate number 6. 2 questions were to be resolved. Was the canopy jettison system adequate for both ground and flight evacuation? Was the Douglas A-4D ejection seat compatible with the F-111 test aircraft? Fully suited dummies were installed in the module. Canopy separation was clean and left no debris in the cockpit. Despite the rather spectacular exit, no significant damage was noted to the flight gear of either of the dummies. Successful demonstration of the interim escape system cleared the way for the on-schedule first flight of the F-111 airplane. Full-scale checkout of the production module's severance devices began in June of 1964, following some 2,000 preliminary design tests. Successful severance from the main fuselage was repeatedly demonstrated with boilerplate number 7, equipped with the basic pyrotechnic system. These successes were duplicated with production components installed on production test pod number 3, in tests culminating in late summer of 1965. Earlier, in October 1964, full-scale sled testing had begun. This program consisted of 2 static launches, as well as the 4 dynamic runs at various speeds, all with boilerplate vehicles. Boilerplate number 7 was launched at 300 knots during February of 1965, part of a series in which severance devices, rocket motor, and recovery chute all performed as expected. The stability vanes evident in this test vehicle were later replaced with a stabilization brake parachute. Zero speed, zero altitude capability remained to be demonstrated, and for this series, boilerplate number 5 was mated to a fixture representing the F-111 crew module interface. Early tests demonstrated excessive pitch-up, but with the center of gravity to thrust line relationship revised to provide nose-down pitching moment, a satisfactory trajectory was achieved. All load factors throughout the trajectory were within human tolerances. Investigation of the aerodynamic characteristics of the crew module continued through the first half of 1965 and included wind tunnel tests at Arnold Engineering Development Center as well as further sled runs. The final test of the boilerplate series, a 300-knot run with boilerplate number 5, was conducted in May of 1965, concluding the full-scale development test program. The work progresses. Now the production test pods take their turn. Production Test Pod 6, used to demonstrate compatibility of production sled and module, has been shipped to Holloman Air Force Base for full-scale qualification tests. Pod number 3 has already undergone many successful severance qualification tests, while Production Test Pod 1 began impact attenuation pre-production tests in mid-December. As 1965 ends, the F-111 crew module escape system becomes a reality, a giant stride toward that ultimate goal of successful escape under all conditions of flight. Another demonstration of design, development, and production capabilities by McDonnell.